I want to briefly tell you why lab math is important, or why I think it's important. And there's one really good example in Gainesville. I see the little cute boy. This is Sebastian. In 2007, Sebastian went to Shands, and he was fine. He was absolutely cute, and he was pretty healthy. He was just a little bit short for his age. So his parents wanted to make sure he's growing all right and there's nothing else really wrong with him. So he underwent a procedure where he had the amino acid arginine injected in his system for an imaging of his brain. Long story short, a set of medical errors caused that he was dead within 48 hours. What happened is that he received about 10 times as much of the amino acid arginine injected into his system, and for a little 3-year-old that was too much and killed him. What happened is that his parents actually, obviously they were very upset, but instead of suing the hospital, they went and created a foundation, the Sebastian Ferrero Foundation, and they collected a lot of money in order to improve facilities for children to be treated at Shands. And if you go by Shands Hospital, go to the children's wing and look at the atrium. It's called the Sebastian Ferrero Atrium, and it's named after Sebastian, who died tragically of a medical error because of 10-fold dilution difference. And I hope something like this will never ever happen in your life to anybody you treat, or anybody in your family, or anybody in your immediate environment. These errors can be avoided, and that's one of the main reasons why I teach lab math and why it's so important for all of you, regardless whether you're going to be a researcher, nurses, doctors, or just parents, to be really informed about what's going on and do the basic math that goes with it. Okay, so I just want to make a couple of things clear for the lab math. I know that a lot of you students struggle with the basic lab math we teach, but I promise a couple of things to you. Lab math won't be more than maybe 5th grade math. So don't be afraid. The math we do is very simple, and the other reason why we do the math is because it's applied. It affects you, your research, your grade, and in the future when you have a job, it can truly save lives. So there are a couple of things I want to go over in lab math, and let's start at the very beginning, at the very basics. Making stock solutions is really important for a lot of experiments you do, and also for downstream when you have diluted. So making stock solutions is actually really simple. There's a couple of different ways. One is where you weigh out something like a salt and do a percent of the volume, or you do a molar concentration, which is going to be next. So the first part is what we just make. For example, as the example says, you make a 1 liter of a 0.9% saline. And that's basically what people inject when you go into the emergency room and you get an IV. That's pretty much what it is. So knowing about that can be really important. What you do have to know is written over here. What we are doing now, we are calculating the weight per volume, because we are weighing out something and we are adding it to a certain volume in percent. So basically, what you also have to know, the most important thing is that in this case, 1 gram of whatever we weigh out equals to 1 milliliter for our calculations. So for example, you want 1 liter of a 0.9% solution. So your total volume, what you end up at the end, your 1000 milliliters, which is the same obviously as 1 liter. And that's equal to your 100%. That's your 100%, your total volume is your 100%. What you want to now know is how much of the volume or how much of the weight is 0.9%. And basically you just do cross multiplication. So you know what your x is, you want to know what your x is, and you write out x equals 1000 milliliters. In this case it will be grams. times 0.9%, and you divide this by 100%. And what you get, if you put this in your calculator, is you get 9 grams, because that's what you need. So you need to weigh out 9 grams and add it to your 1 liter. So you take 1 gram of salt, 9 grams of salt, and add it to 1 liter of water. Here we go. 9 grams of salt to 1 liter of water. So the second way of making solutions is a molar solutions. And instead of weighing out something and putting it into a certain amount of volume, as we did with the weight volume calculations, what we just did before, we now have to weigh out a certain molar concentration. And as you all should remember from chemistry, is that 1 mole is the mass of the atomic weights of each of the atoms in the molecule. For example, sodium chloride has a molecular weight of 58.44. It consists of sodium and chloride, and the individual molecular weights of the molecules are given here, and they add up to this. So this is the molecular weight of sodium chloride, which if you weigh out 58.44 grams, add it to 1 liter, that's a 1 molar solution. And that's really all you need to know. So what I just said is you weigh out 58.44 grams. You add it to 1 liter of water or liquid, and that equals a 1 molar solution. So now your question is, you have to only make 100 milliliters. So what do? 100 milliliters is 1/10 of 1 liter. So if you do 0.1 liter, which is exactly the same as 100 milliliters, you just divide your molecular weight, or your amount of salt, by 1 to 10 as well. And because we use a metric system, it's so easy. You just move the decimal point over 1. So for 1 to 10 dilution, it's 1/10 of the amount what you weighed out before. You just add 5.844 grams into your 0.1 liters, your 100 milliliters, and it's still a 1 molar solution. But now again, look at the question, what you have to do. So you need a 0.1 molar solution. And again, if you see, this is again a 1 to 10 of the 1 molar. 0.1 is 1/10 of a molar. We leave this the same, we leave the volume the same, we can only change 1 parameter at a time. And then again, we divide the weight again by 1 to 10. And if we divide 5.8 by 10, we get 0.5844 grams, which we now add to 0.1 liter, which is 100 milliliters. And we have a 0.1 molar solution. So your result is you add out 0.5844 grams and then add it to 100 milliliters. You should technically take the 0.5 milliliter off. Okay, let's try another one. So again, this is sodium chloride. And let's start again. I always just write it out for myself because I don't get confused. Let's start again. 58.44 gram in 1 liter is 1 molar. So this time we need 500 milliliter. So we divide this by 2. Half. So 0.5 liters, same as 500 milliliters. So again, you have the amount what you have to add in. And half of 58.44 is 29.22. You add this to half a liter and you still have a 1 molar solution. However, this time it asks for 0.05 molar. So to calculate how you make this solution, you take a calculator and you just see what is the dilution factor here. We'll talk about dilution factors in a little bit, but basically you type into your calculator 1 divided by 0.05, and that makes it a 20-fold dilution. So it's a 1 to 20 dilution. Again, you do the same thing with your weight, 1 to 20, and then you type into your calculator 29.22 divided by 20, and it gives you 1.461 grams. Again, it's a 0.5 molar, 0.5 liters, sorry, 0.5 liters. That's why you should always keep the units, and that's your 0.05 molar. So to answer this question here, how you would make a 500 milliliter solution of a 0.05 molar sodium chloride concentration. So you calculate it this way, and then you take 1.461 grams and then add it to your 0.5 liters. And again, what you should do is 0.5 liters minus, which is the same as 500 milliliters, minus 1.4 grams, and technically you should weigh it out into 498.6 grams. Let's talk briefly about dilution, because that's pretty much the underlying factor for many of the calculations we do. Dilutions is basically you take something that's very concentrated and then mix it with more liquid to become less concentration. That's all it is. And you want to often know what the ratio is, how much you have to dilute it, and so on. So the dilution factor is usually the initial concentration divided by the final concentration. And we did the same example just a second ago in the previous example. Remember this formula: dilution factor, initial concentration divided by final concentration. Okay, so for example, if we have 5%, that's our initial concentration, and we want to water it down, dilute it to 1%. That's the final concentration. And in math, or in chemistry, concentration is usually in square brackets. So you basically just do 5 divided by 1, and that's a 5-fold dilution. How would you do that? You take what turns out to be, it's 4 plus 4 parts plus 1 parts. So 5 if your total parts. And then 5 minus 1 is 4, and that's your diluent. And that's your stock solution. So you take 1 part of your original concentration and 4 parts of your diluent. We'll talk about the definitions. And then you mix them together, and then you have your 1 to 5 dilution. What about example 2? So 3 consecutive 1 to 3 dilutions. Make a 1 to 3 dilution, 1 to 3 dilution. And again, your initial concentration is whatever the initial concentration is. You find out later. And then your final, you have to multiply all these dilutions. But to multiply these dilutions, you multiply the numerator and you multiply the denominator. And in this case, is 1 over 3 times 3 is 9, times 3 is 27. So this will be a 1 to 27 dilution. Okay, we've got one more here that's the same as the first example. So think about it. If you have a concentration of 10% and you want to water it down to 2%, how do you go about it? Dilution is really a lot variations of the theme. Once you get the concept, there are a couple of different ways of solving the same problem. Probably the most important formula besides the cross multiplication for the percent at the beginning and that's also where you get your dilution factor, is understanding the formula C1V1 equals C2V2. And most of you should have heard that probably in school and maybe in chemistry. So what it means is that your C1 is the initial concentration of the stock solution. C2 is what you're looking for. Usually the question asks for the either the concentration of your dilution or the volume of what you have to take out. So usually it's this or your V1. Your volume 2 is what you want to dilute it to, and then your volume 1 is what you're taking out of the stock solution to mix it with your diluent. Right, let's try it out. You always just watch out what you have given, what's left over to calculate, and then again you cross multiply and you get the result that way. Okay, so in this case we have a 10% solution, which is concentration 1. We want a 2% solution, which is concentration 2. We need 100 milliliter of the 2%. That's our V2. It's your final concentration, final volume. And we now need to determine V1. Okay, so if we set it up, C1 V1 equals C2 V2. C1 is 10%, and always keep your units. Times X equals 2% times 100 milliliters. Again, you just cross multiply and solve for X. Solve for X, it's 2% times 100 milliliters divided by 10%, and 2 times 200 divided by 10 is 20. So 20 milliliters. What you do, you take 20 milliliters of your original solution. Your V2 is 20 milliliters. And you want a total of 100 milliliter, but you already have 20 milliliters. So you have to subtract your 20 milliliters from your total volume. And so you add your 20 milliliters in 80 milliliters of your diluent. Don't forget to get the final result as what you actually do and how to make your solution. So you always have to subtract the volume of your stock solution from your total volume. Right, let's try the next one. Again, you want to make 100 milliliters, and that's your volume 2 of a 0.01 molar solution. And that's your concentration 2. And you have a 1 molar stock, so that's your concentration 1. So 1 molar times, again you don't know what the volume is, what you want to take out, how many milliliters, equals 0.01 molar times 100 milliliters. Okay, so again you solve for X, 0.01 molar times 100 milliliters divided by 1 molar, and make sure your units stay the same and you always write your units so you don't get confused. So 0.01 times 100 is 1 milliliter divided by 1 molar equals 1, oh, hold on, the molar crosses out, is 1 milliliter. So again, you take out 1 milliliter of your stock and add it to 100 minus 1, which is 99 milliliters of your diluent. So now we're finished with making our stock solution and our dilutions and everything else. So we have everything ready for our experiments. Now we can actually do the experiments. So serial dilutions are often used to see what is the initial concentration in a sample. There can be antibodies, there can be red blood cells, there can be bacteria, yeast, normal cells. So there are lots of ways where serial dilutions are really important, especially when you're working in the lab. But the key thing for serial dilutions is you just multiply all the fractions of each dilution step, what you're doing, and that is your final dilution. So in this case, we saw something like this before. You make 3 consecutive 1 to 3 dilutions. So you make the first 1 to 3 dilution, you have your initial vessel, make a 1 to 3 dilution, make a second 1-3 dilution, and then a third 1-3 dilution. And you should know how to make a 1-3 dilution. A 1-3 dilution is nothing else but 1 part and 2 parts. So 3 total parts, and you add 1 part of your stock and 2 parts of your diluent. Okay? But to calculate the number of the final dilution, you multiply the numerator and you divide it by the multiplication of all the denominators. 3 times 3 times 3. And again, it's always the same thing. It doesn't matter what your dilutions are. And your final product will be 3 times 3 is 9 times 3 is 27. So 3 consecutive 1-3 dilutions is a final dilution of 1-27. Okay, let's try it again. So you make 2 consecutive 1-100 dilutions. 1-100 dilution and another 1-100 dilutions. Think about it. How do you go about calculating it? Same principle. You multiply the top and you multiply the bottom. And because it's metric, you just add zeros. 1, 2, 3, 4 zeros. So it's 1 to 10,000. So 2 consecutive 1-100 dilutions is a 1 to 10,000 final dilution. Pretty simple, but try to practice a little bit more. Alright, this is now real microbiology. We've done all of the other experiments and all of the dilutions to figure out how many CFUs per ml, how many bacteria do we have in a specific sample. Again, it can be the same thing for yeast or for regular cells as well. So our final product here is you have a plate with different colonies on it, right? And you count the different colonies. And you should remember what CFU stands for. So you count the different colonies and you have to know what dilutions you've made. So in this case, from our original sample, in the lab we use saliva for the first experiment. You make dilutions. And a 1 plus 9 is the same as a 1 to 10 dilution, because your total parts is 10 parts and you add 1 part into 10 parts, which is a 1 to 10 dilution. Okay, so you repeat this a couple of times. 1 milliliters and 9 milliliters are 1 to 10. This is another 1 to 10. This is a third 1 to 10, a fourth 1 to 10, and then you plate 1 milliliter probably on your Petrifilm. And you incubate it, and after incubation you find 201 colonies. In this case, because you added 1 milliliter, it's 201 CFU per mil what you put on there, right? So it's in the milliliter you add it to the plate. It's not per total mil. So if you multiply your different dilutions by the number of CFU, what you get is 1 to 10 times 1 times 1 times 1, and again you multiply the bottom, you should know that by now, and you multiply it by your number of colonies you found, and that's what it does. You have 201 times 1, 2, 3, 4, 10 to the 4. But what we need to do now, we need to write it in scientific notation. Scientific notation is always have 1 digit before the decimal point, and then whatever you move the decimal point over, you have to add it to your exponent. So if you have 201, it would be 2.01, and then you add the number to exponent. You have 10 to the 4 here, so it would be 10 to the 6. So for this calculation, your final result is 2.01 times 10 to the 6 CFU per mil. And always remember, our bacteria always counted in CFU per mil all the time.